Why not? Okay. And we have an agenda. Shall I review that briefly? Oh, wrong window. I want to go here and say, I think this is our window for the agenda. Wait, yeah. Oh, but that's a different window? Do I have more than one of these? I guess I do, huh? Okay. So far, all I've got is Kattis warm up and book learning. Um, the calculator. All right. Um, and for the Kattis warm up, we're looking at here permutation descent counts. I don't know. Secure doors. Peg. That seems to be a pretty popular one. Uh, Paul Elegant. Well, let's just pick the permutation. What the heck? And so our first goal is to understand the problem. Seems to be a fairly short statement of the problem. Given an integer, a positive integer n, a permutation order n is a one-to-one and thus onto function from the set of integers 1 to n itself, I guess inclusive then. If p is such a function, we represent the function by a list of values. So I think this is just the basic definition of a permutation, which means a rearrangement of the n elements. So if you had 7 elements, as in this example here, this would be a permutation. So you have all the numbers 1 through 7 in some order, right? And this is a fairly common problem in combinatorics, a very basic combinatorics problem of how many ways are there to do such a thing? Well, there's 7 ways to pick the first. For each of those 7, there's 6 ways to choose the second, so you've got 42 ways to pick the first 2, and then let's see, what are we down to? 5 ways to choose the third. So that'd be 42 times 5, 210 ways to pick the first 3, and then 4 ways to pick the fourth, 3 ways to pick the fifth, 2 ways to pick the sixth, and only 1 way then to finish that off. So for any permutation p, a descent of p is an integer k for which p of k is greater than p of k plus 1. How does one permutation bigger than another? Do we have a comparison operation on permutations? So I see. So it's a number of times as you read from left to right that you get a smaller number, right? So 5, 6, then we go down to 2, so that's 1 descent. We go up to 4, up to 7, then we go down to 1, so that's 2 descents. And then up again, right? So the descent of 2, because 6 is greater than 2 and 7 is greater than 1. I kind of get it. You can raise your hand if you're uncertain, or make a comment in the chat room, or just blurt it out. Okay. Let's get a statement of the problem in our. So I'm going to go to the code window here, and I don't know, what am I looking? Oh, I'm looking at Kenny's program here. So let's exclude that from the project, and we're going to say add a new item, which is going to be Kattis. You can't see that dialog window, huh? Oh, so you can't see me mistyping Kattis. Kattis dash, I'm going to say permutation descent. I don't think that's .cpp. And then I'm going to get the statement of the problem here. Oh, I guess I want to capture just what's on the page, right? And so that's going to go here. Oh, let me put that in a comment box. And okay, so here's I'm just reading off the statement of the problem. One-to-one and undo, that's an isomorphism, as they say in math land. There's a one-to-one correspondence. There's, for each element of the first set, there's a unique element of the second set, and every element of the first set is represented in the second set. So one-to-one and onto. We represent the function by a list of values. I think we can put that here. For example, this is a permutation of the first elements. So 1 goes to 5, 2 goes to 6, 3 goes to 2, and so on. 7 goes to 3. Okay. So for any permutation P, a descent of P is an integer K for which P of K is greater than, for example, the permutation has a descent of 2. Okay, we talked about that. For permutation P, des of P is the number of descents in P. Whoops, okay. Right. The reversing permutation with P of K equals n plus 1 minus K is the only okay, so that you just reverse the order of the elements, right? So that's going to be the only permutation with the descent of n minus 1, right? Because you're going to have, should we just type it in here? 7, 6, 5, 4, 3, 2, 1, and so you've got a descent from 7 to 6, a descent from 6 to 5, descent from 5 to 4. So how many is that? Well, that's 6 descents, one less than the number of elements, right? That kind of makes sense. Okay, so the permutation descent count, PDC for short, for a given order n and value v is the number of permutations p of order n with descent of p equal to v. So, for instance, the permutation descent count of 3, 0 is 1. I'm not understanding this yet. Value v is the number of permutations p of order n. Okay. Order n. Given order n. So I guess that's the first parameter here. And value v, so that must be the second parameter. So permutation of order 3 with 0 descents. Well, there's only 1, right? So that's 1, 2, 3. If you're going to have 1 descent, how many different ones are there with 1 descent? Well, 1, 3, 2, 2, 1, 3, 2, 3, 1, and 3, 1, 2. Kind of missing a bracket here, aren't they? Put that in. And there's only one permutation of 3 elements with 2 descents, right? And that's the reversal. All right, kind of getting that? Alfredo, could you please mute your mic until you need to use it? Getting lots of noise here. Yeah. Sure, no problem. Okay, so write a program to compute the PDC for inputs n and v. To avoid having to deal with very large numbers, your answers should and your intermediate calculations will be computed modulo what? That's 1,001,113. So be it. Ours is not to ask why. Ours is to accept our Kattis without complaint. So the first line, so the input is going to be a single number p between 1 and 1,000, which is the number of data sets that follow. Each data set should be processed identically and independently. Each data set consists of a single line of input, contains the data set number k, followed by the integer, or you can't read what I'm looking at here. I should perhaps, what can I do? I can narrow my window so I'm sure I'm not, there we go. Okay. Each data set consists of a single line of input. It contains the data set number k, followed by the integer order n, followed by the integer value v, which is between 0 and n minus 1 inclusive. And for each data set, there is a single line of output. The single output line consists of the data set number k. That's easy enough, right? That's sort of a common thing for Kattis to do, is just have you number things. Followed by a single space, followed by the PDC of n and v as a decimal integer modulo 1 million blah blah blah. Okay, so here's some sample input and output. And I'm not sure how, so if the input is 4 followed by 4 data sets, there they are, right? Then the output is going to be, I guess, I'm not sure what I'm looking at here. Okay, so right. So there's 4 lines of output here. So the first number tells you how many data sets you've got. Then these are just, these numbers here are just, you know, counting which data set it is, right? And they're the same as these numbers here. Okay, so 3, 1. So how many permutations of 3 elements have 1 descent? And we saw that there are 4, right? Those are actually spelled out here, right? The second data input is 5, 2, which means how many permutations of 5 elements have 2 descents, and 66. I'm thinking, do I want to actually kind of move this down a notch? Can I do that? No. All right, no problem. Just so that they line up, I know. That's probably obsessive, but okay. So 5, 2 gives us 66 ways. Should we write them out? Oh, that would be tedious. Should we write out a few of them? How about over here? Just, you know, just to get the flavor of it, right? So 2 descents, huh? So we could have 5, 1, 4, and if I were to put a 3, then I'd have to have a 2, right? So I'll put a 2 and then a 3. All right, so that's 1 permutation of 5 elements with 2 descents, right? Should we have another one? How about, just to get the flavor of this, right? 4, 3, 5, 1, 5, 1, 2. Oh yes, permutations, which it's an interesting problem. Thank you, Kattis, for a nice, interesting problem. Okay, and okay, so now permutations of 8. How many permutations of 8 are there? 8 factorial, right? So let's make a note. There are 8 factorial, which is a big number. 5,040? No. Well, let's see. 3 factorial is 6. Oh, let's make a table here, right? So I can say n factorial and 0, 1, 1, 1, 2, 2, 3, 6, right? 3 times 2 is 6. 4, 24. Whoops. Yeah. You just keep multiplying the previous number by like 5 times 24 is 5 factorial, right? It's 5 times 4 factorial. That's 120. 6 factorial is 720. 7 factorial is then this 5,040, I believe. And then 8 factorial is going to be 40,320. Right? Of which apparently 15,619 have 3 descents? For example, just so we make sure that we're understanding the problem, right? So give me a permutation of 8 elements that has 3 descents. Well, 8 1 7 2 6 3 4 5. All right, so I take care of the descents at the beginning. 8 1 is a descent, 7 2 is a descent, 6 3 is a descent, and those are my 3 descents. So then I just get bigger from there. We can get another one fairly easily. Could we just take this 3 4 5, put it at the beginning, right, and then have that followed by the 3 descents? So we could go like 3 4 5, then so that's all getting bigger. Then 8 1 8 1 7 2 6. Oh, hold on. Oh no, that's 6 3, huh? So you put the 4 5 and then the 6 3. Just trying to get a flavor for this, right? So 1 descent, 2 descents, 3 descents here, and then the same 8 1 descent, the same 7 2 descent, the same 6 3 descent here. Okay. Okay. I guess that kind of completes my commentary there. So do we have a plan? I don't have a plan. Yeah. I mean, with factorials, you know, the numbers get very large. I think, in fact, the factorial function's rate of increase is eventually larger than the exponential rate of increase, I believe. Yeah. Why? Well, if you have, you know, n to a power p, you just keep multiplying by n, right? But if you have n factorial, the number you're multiplying by gets larger. I don't know. It's not a very good explanation of that, but so, well, let's kill some time by including the usual suspects. And what are we going to need? Like vectors, maybe? Is there a permutation? Maybe there's a library we could use, but well, I guess so. You'd want to have this PDC function, right? Or how about just a descents function? Huh. Um, so well, let's throw in the vector library and okay. Well, let's start by writing the so we have this des of p, right? Where p is a permutation. How are we going to represent our permutation? Do we want it as a vector? I guess we do want it as a vector, right? I mean, we've been writing them as little strings here. In fact, I wasn't even separating them with a space here, right? Just for economy. But as soon as you get two-digit numbers, that starts to confuse things, right? So yeah, I guess so. The container for a permutation would be a vector, perhaps. So we can have it. So the sub goal define des of p, right? So that's going to be a function that takes a vector. I guess that's the container we'll use as a vector of integers. And so it's going to take a vector of int objects, v, I guess, and return an int. And let's, use good form here. So we'll have our main function in here, and then we'll define, this is a prototype here, right? So we need a definition for that prototype, and put it down here. So I guess we'll have an integer count. Yeah, this is that the best type to use for something that's counting, right? Because an integer could be negative, and so you might say, well, it should be unsigned. Yeah, there's this thing called, and maybe this deserves a little discussion. There's something called size t, size underscore t. And so when you think of a size, that can't be negative, right? Sizes are always positive. So how does size t compare with int, and what is it used for? I guess I need to change my prototype here. If I'm going to use size t as the return type. Well, let's do a little search on that subject. So here we are in the browser. Okay, and I guess this is our yeah. I don't know. So I'm going to look at size underscore t versus int in C++, and unsized int versus size t is a discussion on Stack Overflow. It's also there's a forum discussion in C++.com. Let's go with this unsigned int versus size t, which was asked 11 and a half years ago and archived 8 months ago, viewed 201,000 times at least. And so the question is, I noticed in modern C and C++, that modern C and C++ code seems to use this size t instead of int or unsigned int pretty much everywhere, from parameters for C string functions to the STL, the standard template library. I am curious as to the reason for this and the benefits it brings. Well, good for you. It's good to be curious. And here's 304 people approving of this answer here. The next answer only has 100 approvals. So who is this that's responding here? Craig M. Brandenburg, who you can take a quick look. He's in Scottsdale, Arizona. Programs low-level languages. Go and Rust are other low-level languages aside from C++. Okay. And he says the size t type is the unsigned integer type that is the result of the size of operator and the offset of operator. So it is guaranteed to be big enough to contain the size of the biggest object your system can handle. Yeah. For example, a static array of 8 gigabytes. Size t. The size t type may be bigger than, equal to, or smaller than an unsigned int, and your compiler might make assumptions about it for optimization. You may find more precise information in the C99 standard version 7.17, a draft of which is available on the internet in PDF format. Well, that would be going too deep, wouldn't it? But let's try this size t thing, and there's some other comments. Nope. Nope. What does that mean, nope? Think of x86-16 with the large, not huge memory model. Pointers are far 32-bit, but individual objects are limited to 64K, so size t can be 16-bit. Yeah, some people are objecting to this wording. However, the idea is correct. The size of an object can be much more limited than the address space. Your compiler might make assumptions about it. A quote here. I would hope the compiler knows the exact range of values that size t can represent. If it doesn't, who does? All right. Somebody responds to Mark here. I think the point was more the compiler might be able to do something with that knowledge. All right, well, I guess this is getting to be a little esoteric. So we're going to try using that and see how it goes. It's very similar to unsigned int. All right. So, and currently it's initialized to 0, right? And so what do we want to do? We want to walk through our vector. So for, I guess we're reading from left to right, yeah? So, I guess shall we have our first how about start? I'm going to call it start. I don't know what else to call it. The idea being that start actually should be assigned the value of v of 0, right? Presumably it's not an empty vector, right? And so I'm going to say for int I equals 1, I guess, because I want to get to the next one, right? I less than v dot size, increment I. So we're going to walk through this array, and we're going to say if, I guess we can have more than one statement here, so let's anticipate that. If what? If v of I is less than start, Should we call it current? Just to give it a better name. So if v of I is less than current, then we're going to increment count. Then what are we going to do? We're going to say current equals v of I. There's probably a more efficient way of doing this. I'm just getting it done. All right, so should we test this thing out? So yeah, what is main going to do? It's going to read the number of test cases, right? So let's have using my fancy new type, size t, and n, and we're going to read that from the input, right? Then I'm going to say while n and post decrement operator, and so then we're going to get the next integer, which is going to be, shall we call it k? I think that's what they called it. Do we really have to look at all permutations? Because there's going to be a huge number of permutations for, fairly small numbers, like, 20 factorial is already gigundo, right? So while we can so we're going to look at each test case, right? So, and then we're going to get another number, right, which is the, what is that? I don't know, list? List is a bad word for it. Item? Which item is it? Okay. And maybe that should start at 1. Because we're gonna C in item followed by k, right? And then we're gonna C out really feel like we should probably do more pencil and paper work, right? But let's so can we get a random permutation? How would you make a random permutation? I think there's probably a function for that. So let's yeah, okay. I'm going to look for that on the interwebs. So I'm going to the browser, and I'm going to look for C++ STL permutation of a vector, maybe? I don't know. Next permutation and previous permutation. Sounds like a good thing. It's in the standard library. This is Geeks for Geeks. And they've got a little advertisement here. It is used to rearrange the elements, into the next lexicographically greater permutation. A permutation is each one of the n factorial possible arrangements the elements can take, where n is the number of elements in the range. Different permutations can be ordered according to how they compare lexicographically to each other. Okay. So it's a template function. It's returning a bool, true or false, and the function is called next permutation, and it takes a bidirectional iterator. Oh, what's that? Well, it's one that can go forwards and backwards. And it's what is an iterator? Well, it's a pointer to an element of a container. right? And what's a container? Well, a vector is a container, right? And so first and last, right? So you want to get the next permutation. Well, so the parameters first and last bidirectional iterators to the initial and final positions in the sequence. The range used is first last, which contains all the elements between first and last, including the element pointed by the first, but not the element pointed by the last, right? That's that half-open interval kind of thing. So the square bracket means included, the parenthesis means not included. So the return value, if the function could rearrange the object as a lexicographically greater permutation, it'll return true. Otherwise, the function returns false to indicate that the arrangement is not greater than the previous. What does it mean, greater than? The next lexicographically greater than value for example. The next permutation of 1, 2, 3 is 1, 3, 2. And we know that 1, 3, 2 is greater than 1, 2, 3 because 3 is greater than 2? Yeah. The next permutation of 4, 6, 8 would be then 4, 8, 6 because 8 is greater than 6, right? And here's a little program to illustrate this. Notice that we're including algorithm, which is where you're going to find this function. And so well, should we just grab this and see how it works in our space? So I'm going to go back to the code window. Yeah. Okay. And we want to include algorithm. And what should we do with this code that's now in the clipboard? I don't know. I can just put it in here, huh? Oh, yeah. I guess I didn't want all that. I'm going to go back here and just grab the innards of that. Okay, so they're taking an array of 3 elements, and they're sorting the array so that it's, you know, in increasing order. And then it says, see out the 3 factorial permutations are so you print out, and then so this is just printing out the so I'm just wondering, do we have to have an array, or can we use a vector container instead? I suppose the array wouldn't be bad, huh? I tend to prefer to use vector containers, but notice that the next permutation is actually going to affect this array object, right? Okay. So let's comment out my code here that I was writing and just take a look at how this works here. Can we run this? Oh, it's got some Unicode characters. Do you want to resave this file as Unicode in order to maintain your data? Well, I'm not sure. How about no? And then here, my des function, there's a problem with it. What's the error? Yeah, you can read that, right? Must return a value. Okay. So we're going to return count. Do I want to say yes or no? You can't see that dialog box. It's okay. Let's go to the output window, and you see the 6 possible? So this would be one way of getting all the permutations and just counting them? Is that cheating? Yeah, it's using the, but I'm just sort of worried that there are so many that it's going to take for bleeding ever. Uh, hmm. Well, um, should we try it? So let's try to make this work, and if it doesn't, then we're going to have to get clever, right? But this is sort of a, um, what do they call it? Method of exhaustion. The um, brute force is what it's called, right? When you just look at every possible case and count it, right? So I guess, can we do this with a vector? I guess is the next question. I think we can. So let's. Um, right. It's exactly what was going through my mind, which is an array. You can allocate memory on the heap for an array, in which case you can have it with a variable size, but that's beyond where we are. Um, and vectors are designed to do exactly this sort of thing. So let's go with that. So I'm going to say I've got a vector of ints called array. Oh, yeah. Well, let's can we do it? Let's just like that. Oh, you can't see that. Yeah. I see that I've got a problem now. So I think I have to put an iterator here and the name of a vector. See, that's the nice thing about arrays. The name of the array is a pointer to the first element in the array, and that makes it an iterator. And the name of a vector of ints is not uh, a pointer to the first element of that vector. So how can we get a pointer to the, well, we can just say, give me the address in memory of the first element. And then give me the address of the first element plus array.size. Okay. And so then down here, I would want to do the same thing. I think I'm missing a parenthesis or something, right? Yeah. Okay, so we've adapted this to. So this should work, right? Let's try it. So if I go, you can't see that dialog window. It's complaining about the Unicode characters. And so here's the output. And you can see, okay, so now that we have a vector of ints, we've adapted it to use this next permutation thing. And so we basically just want to count for each one. Brute force, huh? This is going to get ugly, though. Okay, well, let's bring back our code here. And I think that should go at the beginning. Oh, you can't see what I'm doing. Sorry. So I'm going to put this here. So I get the item number. I'm going to see out the item number. And I guess that's all for now. Followed by a space, maybe. Yeah. And then I need to compute this thing, which is the number of descents. Um, can I do a Control K, Control D just to clean up the indentations? Yeah, that's the shortcut to apply the stylistic correctness. All right. So I get K, and I have to use K to build my array, right? So is there some easy way of, probably there is, right? Of just, having it be 1 through K rather than a hardwired 1 through 3 here. But I'm just going to make a little function called initialize, and it's going to return a vector of ints. I know, there's probably a better way of doing this. Initialize, and it's going to take an int k. I suppose we could use the size underscore t. And I'm just going to say for int I equals 1, I less than k, less than or equal to k, I guess. I don't know. Increment I, and oh, we're gonna want to have a vector of ints, right, to return return value. So it's an empty vector now. I suppose we could have, if we had put a k here, that would give us a vector of k elements, all zeros, right? And it seems like an obvious sort of thing to want to load up a vector 1, 2, 3 up to k, right? But there's no default constructor for that, is there? I don't think so, right? You can have the same element, but not different elements. All right, whatever. There's probably some built-in somewhere or something, but we'll just do it here this way. And so I'm going to say return value of, I guess, I minus 1, right, is going to be the index, is going to be equal to I. Or I suppose, I could have done it. Does it matter? I could have done it this way, right? Strictly less than k, and then have this equal to I plus 1. Either way, right? So then we're going to return value. Okay. And so down here, this is going to be initialize of k. I guess we're going to be doing this repeatedly, right? So before doing that, so we read the, where are we here? So we read the 1, 3, 1, right? Oh, I didn't get the third number, did I? And what is that third number? It's the number of descents, right? I don't know what to call that. How about something descriptive, like descents? So this is just the item number, I guess, which, item is a little vague. I'd like to use descriptive variable names, but sometimes it just feels dumb. Okay, so we have descents, and we're going to read that in too, right? Okay. Okay, so at this stage we've got, should we make a little comment here? This is going to be 1, 2, dot, 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 up to k, right? That's going to be our vector. And that is the smallest lexicographically possible, right? So a permutation of these elements. So we don't need to sort it now, right? Because we've already got it in sorted order. So let's just, I don't know, do we delete that or just comment it out for now, huh? So there are k factorial permutations with k elements, right? And so we're going to, we don't really need to like print them out, although it wouldn't be bad, huh? So do have a little for loop here. For int I in, what's our thing called? R? Cout. I just want to see that this is working, right? Obviously this is not what Kattis wants, but on the road to Kattis pleasure we have many pit stops. So cout I followed by a space, I guess. So for every integer I in our vector R, short for arrangements, array, we're going to have each one print out. Okay. Then we're going to get the next permutation, and print that one out. Okay. So if we run this thing now, does it compile? No. I've got local function definitions are illegal. Oh, I think I've got a bad, I need, I did another control K, control D there to, okay, so let's see, does it compile now? Okay, so if I go to the output window, it's waiting for input, right? So I'm going to say 1, hello, 1, okay, followed by 1, 3, 2. Okay, well, so we see the permutations of 3 elements, right? 1, 2, 3, 1, 3, 2. 2, 1, 3 would be then the next one, right? And then 2, 3, 1, and then 3, 1, 2, and 3, 2, 1, right? Nice little function, huh? I wonder how that works. How do you get the next permutation? What if you wanted to look that up? Could you? Should we? Let's go to our browser. Do they give us any more information about how this thing works? So the name of the function is next per. Oh, there's also a previous permutation, but we just want this next permutation one, right? So what if we go to standard template library, next permutation API, something like that. So there's something in C++ reference. So this just describes what it does, right? It doesn't describe how it does it. There's also the comparison operator here. Yeah, there's probably some way of finding out exactly how it works, but do we care? Mutates the range first last to the next permutation, but how? Okay, so here's some source code for it. Yeah. If first is not equal to last, if there's anything in the range, then we declare I to be a bidirectional iterator equal to last. And if you got something on GitHub, yeah. Oh, Microsoft's STL is open source now? I would think so. Microsoft. Okay, I'll take a look at that. But that last thing was actually looking, oh, okay, so algorithm standard header, Microsoft Corporation. So, oh, okay. Optimistic temporary buffer. Yeah, it's a template function. Let's see, find next. I guess there are a lot of nexts in here. I guess I should look for next permutation, huh? It doesn't a misspelling. Oh, there it is. Okay, so there's the function template for next permutation. Yeah, if you wanted to. Oh yeah, it's doing a little swap. Okay, so. Yeah. All right. Well, let's just accept that it does what we want it to do, right? Because this is just the warm-up after all. So where am I? I'm in a balloon over here. Okay, so we're gonna, brute force. We're going to walk through each of the myriad mini permutations, count the descent number. If it's equal to our number, then we increase our count. Okay, so so this is our descent function, and so we're going to have another function that calls the descent function. Well, no, actually, yeah, I think that's okay. So where are we here? Okay, so we're walking through each of our test cases. We're getting that line of input. We're spitting back the item number, creating an array of k elements, and then instead of doing this, which I'm just going to delete that and say, so this is a little do loop that will walk through each permutation, right? And we don't actually want to show the permutation here. We don't really care about what the permutation is. We just want to say if descent of R is equal to descents, then, you know, do some counter. Let's see, I need another variable, don't I? Okay, shall I put it up here? I'll just call it counter. And I guess we'll reset counter to 0 here. And then if that is true, then we're going to increment counter. And after we've done all of those, we're going to see out counter followed by an end line. I don't know. That's my plan. I'm sticking to it. So, should we get some sample input here? I'm seeing I have a piece of crud on my keyboard. Excuse me a moment while I... Oh. Okay. All right. Oh, how did that plus sign get there? Okay, so I want to get this input here. Okay, Control C. Then I'm going to run the program. Okay, it's not complaining about the Unicode anymore. That's good. Let's go to the output window here. And is that the right stuff? Well, let me grab this and I'll paste it into our code so we can study it. So code is here, and stop the program from running. And so what I saw, my output was, well, this was the input, right? Oh, I see. So 4, then 131, I get the output 14. That's good. 252, I get the output 260. Wow, okay. 383, I get the output 315,619. That's good. And 499.50, I don't get any output at all. I get the 4, but I don't get this 325,091. So what are we looking at with that one? That's if you have 99 elements in your array, the numbers 1 through 99, and you want to count how many have 50 descents. That's a large number. So I think our problem is not so much that it's a large number. Also, there was what was this other number? This number here. We want to compute this modulo, whatever that number is, right? Yeah. So where does that fit into our code? I think let's make that a constant up here. So I'm going to say constant int max equals this thing, and so the problem is this counter where we have a count. It's the number of descents. That's never going to be huge, right? But the number of times you get that number of descents could be huge. I don't know. Put the little modulo max there. Oh, wait, what? We do have a max. It doesn't know how to do that. How come it doesn't know max? Let's hover over there. Max is ambiguous. Oh, yeah. Okay, so what do you call this thing? Spillover? I don't know. There. That shouldn't be ambiguous. I don't know how good a name that is, but yeah, I guess max is one of those words that tends to get used a lot by different libraries, even though it's not a keyword. I don't believe. Or maybe it is. Probably not, I'm thinking, but we could look at the keywords. Shall we look at your browser? So we'll look at C++ keywords. You see max in there? No. It's in alphabetical order. And it goes long mutable. Okay. So back to our code. Namespace collision? Yeah, right. With what? Yeah, probably with this algorithm library, right? Yeah. So I'm sure max is a keyword or not a keyword per se, but a reserved word. Yeah, it's part of the algorithm namespace, perhaps. And so, yeah. Well, so what do we have? How come we didn't get that last result, I guess? So we're saying it actually, we did spit out the 4, right? So we got the item number, and then we initialized a vector of 99 elements. We set counter to 0. We say if the descent count of our arrangement equals descents, then increment the counter. And I get a little worried here that we're going to get spillover, right? So that was the whole reason for spillover. So we can just keep doing that as we go, right? That might be overkill. In which case we don't need this here, right? We would already have done that. So I'm trying to think why. Okay, so let me try this again, see what happens. I want this input here. Whoops. Control C, and I'm going to compile and run. And yeah, it's not getting that last. You suppose it's still thinking about it? I'm just not being patient, right? How many permutations of 99 things are there? 99 factorial beers on the wall. You take one down, you wait a long time. You suppose that's what it's doing? Right. See, this is where we reached the fail stage because we weren't clever. We just went through with brute force, and brute force with 99 factorial. Good God, that's going to be a large number. Can I get my calculator visible here? Let me try that. If I go here, that's my calculator, right? So I want to add a new window. Yeah. So if I go back to, it's not clear to me. Okay, if I go code, do I want to have a calculator? I can make a separate scene for the calculator. Okay, so let me do that. I'm going to say the name of this is calculator. I'm working in OBS now, right? I'm going to say OK, and in calculator, I want to add a source. I'm going to say window capture, and I'm going to name it calculator. Microsoft calculator. And I'm going to say OK, and then I'm going to search for the calculator in my list of, oh, there it is. Okay. So I'll say OK here, and I don't know, you can't see the calculator. Nope, not a thing. I wonder why. Yeah, over here it's just empty. Well, let's go back to the output window. Still thinking about it, you think? I mean, yeah. So, but if I go to my calculator, whoop, I need to clear this out. Say 99 n factorial. Yeah, it's yeah. Let me go ahead and copy that and go to our code. Still thinking about it, right? So it's still running, right? That's why we're not seeing anything here. But if I go, let's see, where can I? Okay. So let's make a little note here. This is 99 factorial. And that E155 means 10 to the 155th power, right? So it's not surprising. So we need a more clever. Brute force is not going to do it. We tried brute force and failed, right? So let's make a little comment here about that. So brute force is a fail. All right, it worked fine if, 8, that was no problem, but 99, not going to happen. So maybe we need to say that we're warmed up, but we haven't solved the Kattis problem. There's got to be a more clever way of doing it, right? So should we try just try working this one by hand? 8's not too bad. Oh God, there's a lot with 8. How about what if the input were 5 elements? How about just 4? There's only 24 permutations of 4. And we can maybe make a tree of values. So what is it? PDC of I don't know, 2, 0. Is that a thing? So that means no descents. There's only one of those. PDC of 2, 1 is 1. There's only 2 permutations, and so that's of 2 things. So that's all of them, right? So PDC of 3, 0, that's going to be equal to 1. Looking for a pattern here, right? 3, 1. Sorry, 3, 1. Isn't this, that's the one that turned out to be 4, right? Yeah. We listed them out up here somewhere. Right, yeah, PDC of 3, 1. There they are, right? Alrighty, and PDC of 3, 2 is just 1. Okay, PDC of 4, 0, that's again 1. What is it? To be sure, right? That's going to be 1, 2, 3, 4, right? PDC of 4, 1, well, about 1, 2, 4, 3. That's got 1 descent, right? 1, 3, 2, 4. That's got 1 descent. 1, 4, 2, 3. It's a different one, right? I'm just, I'm not using any real logic here, just kind of throwing permutations against the wall, seeing if they stick. So those are all the ones with 1 as the first element. 4, 3, 3, 2, 4, 2. So another way of getting about 1, 3, 4, 2. Yeah. Oh, we don't have that, do we? 1, 3, 4, 2. So there seems to be 4 with 1 as the first element. And that kind of makes sense since you're holding the 1 fixed, right? And so you're looking at the 4 ways to permute 2, 3, 4, which is kind of like this value here, right? 4 ways to permute 3 things so that there's 1 descent. All right, so if the 1 is in the first position, we get those, right? So what if the 2 is in the first position? Well, then you have the possibility of having a descent, right? If there's 1 in the first position, there's no way to descend from there, right? If you have a 2 in the first position, then you could have a descent right away, right? And then 3, 4 would be the only way to finish that, right? If you have a 2 in the first position and you don't have a descent right away, like say 3, then you'd have to go 4, 1 would give you 1 descent, right? Another one with 2 in the first position. 2, 4, 1, 3. That's 1 descent, right? Let's maybe put all these ones with 2 together here. Kind of looking for a pattern. Oops. 2, 3, 4, 1, 2, 4, 1, 3. Okay. Are there other ones with 2 in the first position? 2, comma. So we have 2, 1, 2, 3, 2, 4. So if it's 2, 1, is there another way to get a single descent? Oh, that's already a single descent, right? So there's no other way to, yeah. So, so 2, 3, is there another way to get, yeah, you could go 2, 3, 1, 4, right? So you descend from 3 to 1, but then not to 4. So there's two that start with 2, 3. You either have the descent after the 3 or not. But that's it for 2, 3, right? So 2, 4, is there another way to get a single descent starting with 2, 4? Well, yeah, 2, 4, no, there isn't, huh? Well, that's interesting. So there's 4 of those. Was 2 first, right? What if they have 3 first? 3, 1, 2, 4. That's it for starting with 3, 1, right? So how about 3, 2, 1? Oh no, that's 2 descents, right? So if we go 3, 2, then you're going to have one more descent, right? So there's not another, or there is no 3, 2, huh? 3, 4, 1, 2. Okay. Those are all the ones starting with 3. So there's only 2 starting with 3. So there's 4 starting with 1. There's 4 starting with 2. But only 2's, unless I'm missing one, right? 3, 4, 3. Yeah, I can't have 3, 2, right? Because then you'd either have a 1, 4, in which case you have a fail, or a 4, 1, which would be a fail. So is there one starting with 4? 4, 1, 2, 3. I think that's the only one, right? Because 4, 2, 3, 1, that would be 2, 4. Yeah. So what are we saying here then? There are 11? Seriously? Should we could test that, right? By running the program and saying I got 1 and 4, 1 is, so I want to get 11, right? Okay. 5. The output is here. I'm going to say I've got 1 test case, and it's the number is 1, and it's 4, 1. Do I get 11? Yeah. Okay. Not that that's given me a great amount of insight. All right. But, you know, it has started shedding some insight on this problem, which brute force will not do the trick. So it's 11, huh? I guess the next, you know, I know, I should just let go, right? PDC of 4, 2. So now we want 2 descents. If we start out with a 1, then it's going to have to be 4, 3, 2, right? So there's only one that starts with a 1. Starts with a 2. We could go down and then 4, 3. Is there another one that starts with a 2? Yeah, we could have 2, 3. No. You have 2, 4, 3, 1. But you can't start with 2, 3. Or can you? I suppose we could run the program and see what we should get. But we're trying to work out the logic of it. Okay, well, I'll just leave this out. I'm not married to nailing this down at the moment. We can come back to it, but I think we've explored the problem-solving approach to this, and discovered that brute force not going to work. Need something a little bit more elegant, maybe something recursive, right? I mean, we do see this kind of recursive nature creeping in here. If the first one is a 1, then it's, you get the same as if it were 3, 1. So is there some way of saying 4, 1 is the sum of, 4 plus 4 plus 2 plus 1? Yeah. There's the I mean, you could okay, I'm not ready to let it go. I kind of want to just sort of look for a pattern. So what can I do? I can say I've got all the test cases with 4, right? So I can say, what are the, if there are 4 elements, I could say 1, 4, 0, 1, 4, 1, 1, 4, 2, and 1, 4, 3. And that's going to be 4 things to consider, right? So I'm going to run that. It's my output window. So I'm going to say I've got 4 test cases, and they're 1, 4, 0, 1, 4, 1, 1, 4, 2. Oh, that's also 11. 1, 4, 3. That should be 1, right? Okay, so I'm now seeing that there's kind of a pattern here, right? There's symmetry. Let me record that output there. Where? How about down here? Okay. So with 5, there's going to be 5, right? So let's run that. So here's my output window. I'm going to say there are 5 test cases. 1, 5, 0. That's going to be 1. 1, 5, 1. That's going to be 26, of course. Sure. 1, 5, 2. Obviously 66. 1, 5, 3. 26 again, right? And this is sort of probably obvious symmetry, right? Record that result. So we see the numbers 126, 66. So I'm going to record these in sort of a Pascal's kind of triangle sort of thing. So we got 1, 4, 1 if there's 3. 1, 11, 11, 1 if there's 4. 1, 26. I'm writing down. I wish I had my. Can you see the? No, you can't. Oh. You can kind of make out something there. Yeah, I need to get my Elmo working here. But yeah, you can kind of see 126.66, 26.1, right? Nothing at all jumps out at me there. I mean, um, 11 was twice 4 plus 2 plus 1. 26? Is that going to be twice 11 plus 3 plus 1? I don't know. And then what the hell is the 66? Looks like 6 times 11. All right, one more of these, and then I swear I'll give it a rest. So 5. Sorry, I'm compile and run. Go to my output window. I'm going to say I've got 6. And the first one is 160, right? And then 161. Then 162. Oh, it doesn't matter what the first number is, right? 6, 3. Well, really, if I was counting, I would go, this is 363, right? 4, 6, 4. And there it is, right? That symmetry. And 5, 6, 5. So yeah, we get to the next row in my so-called Pascal's pseudo-Pascal triangle is 157, 302, 302 again, 57 again, and 1 again. All right. So let's go. I know I'm not done. I'm going to do one other thing, which is something that's pretty cool. Which you may or may not know of this. There's something called the Internet Dictionary. Integer sequences. Is that the right thing? Online Encyclopedia of Integer Sequence. That's the OEIS, right? Okay. So if we go there, see, I'd enter in a sequence, and it'll tell you what that is, right? So what sequence am I going to enter? Well, I'm going to look at you know, the sequence of 3 choose 1, 4 choose 1, 5 choose 1, and 6 choose 1. Or that is PDC of 6, 1, right? And see if that gives me a recognizable sequence. So 1, 4, 11, 26, 57. And it says, oh, these are obviously the Eulerian numbers. What? So the next one would be 120, then 247, 502, and what are the kinds? There are 2 versions of Euler's triangle. Classic version of Euler's triangle used by Comtet, and the version of Euler's triangle used by Graham, Knuth, and Potashnik. Yeah, you knew Knuth was going to be in here. In concrete math. I have this book. Pretty good book. I recommend it. for computer science people. Um, and Euler's triangle rose. So should we look up Euler's triangle? It appears to be a thing. Right, so non-zero terms of the sequence can be found from the row sums of the third subtriangle extracted from Pascal's triangle. Oh, okay. Okay. So there's a lot to say about. Yeah, rabbit hole time. Um, Asymptotic behavior, the one-dimensional rock, paper, scissors, cyclic cellular automaton. Oh, that sounds like a nice project. Okay, well, so shall we look up Euler's triangle? You've heard of Pascal's triangle. I'll bet you didn't know that Euler had a triangle. Oh, not that triangle. The Euler line of a triangle. Yeah, no, this is a numerical thing, not a geometric thing. Triangles. Okay, next. Euler line. Well, okay, I think we'll come back. Well, I guess if we go back to here, what are the next numbers? Right, so 120. Should we check that? So if you go back to the code, I'm gonna, I guess, grab these numbers here and add them to my list of outputs here. Okay, there's that 57302. Then I want to go one more time here for the good times, and I get 7 and 170. That's going to be a 1, obviously, right? 272. That's going to be 1191. Well, that's not 120, is it? So 373, 2416, and 474 should be that 1191 repeated again, right? 575. Oh, there's 120. Wait. Oh, I skipped over the first one, didn't I? That was a boo-boo. So if I put in the 671, that's 120, right? Okay. Do I want another one? 776. It's going to be 1 again. So these are not in the right order, but look at that. There's that 120. That's pretty damning. What did the Internet Encyclopedia of Internet Integer Sequences say it should be the next one? 247? Okay. I'm going to take this and add it to my list of suspicious evidence. Puzzling evidence. And go one more time. I'm going to say got 8. Well, we only need 4 with 8, right? Because we have the symmetry working for us. So 4, and we're going to say 1, 8. Well, we really only care. 247. Yeah, that was the next Euler number, right? So then 282 and 383. There's that number again, huh? We've seen that number before. 484, and it's going to be that. So, well, this is kind of fun. So 247, huh? And if you go back to that, there it is, right? 247. That can't be a coinky dinky. All right. So, is there a formula for the nth triangular number? And yeah, also notice um, this. Oh, I didn't mean to do that. This 15,619. Is it, so that's, oh, that was, yeah. That was 8-3, right? Yeah. So that's not a coincidence. That's just another incidence. Okay. All right. So if we go to our browser one more time, just I promise to let this go. We're going to look for formula nth Euler number and Euler's triangle. See, the problem with Euler's triangle is that there's a very well-known geometric so Bernoulli numbers. So this is International Journal of Pure and Applied Mathematics. The Bernoulli numbers are a sequence of rational numbers applied in various mathematical fields. It can be written as a limit with t tending towards 0 applied to the nth derivative of this function. Oh, okay. Well, that's a little bit beyond our ken, isn't it? So, and this is just a link back to the Encyclopedia of Integer Sequences, but they have a more interesting thing here. Euler triangle and figure-it number recursion. Do they have a formula? Oh, Pengli, I know this guy. He's at New Mexico State. I think he's retired now. Okay. Well, we'll come back to this. Let's go back to. Sorry for that diversion. What was our plan today? Oh, book learning. Right. So let's get started on that. Then it would be about time to take a break, right? But so any questions about any observations about this Kattis problem? Turned out to be more interesting than we deserved. Okay. So see nothing. I will go. Let's go to discussions. I did post up some things last week. Oh well, there is the SIR program. That should be a pretty slow softball. I guess there are things we could talk about there, such as the accuracy of the model. I mean, there's so many people doing computer models of things and then dictating public policy based on computer models. One that comes to mind is the global warming business, where many computer models are used to predict what's going on with carbon dioxide and whatnot in the atmosphere, and the models don't seem to fit reality, and so they keep changing the models, and it's a constant interplay. In any case, we have Stroop exercises 6.2 and 6.3, and I did a video on that, right? Which you are welcome to watch. But let's get that up on the workbench here, and you can see what we did with those exercises, and then maybe move on, and then definitely move on So where am I? I want to exclude this from the project. It'll probably ask me to save it, and yes, um, we will get that thing. We're not going to leave it forever, but I'll work on it on your own time and let me know if you come up with some brilliant way of. I think it's got to be recursive somehow, right? Yeah. All right. Um, it's hard to let go, isn't it? I'm going to add an existing item here, which is going to be the buggy calculator. It says here I last worked on this April 5th. Actually, the dates on these things are misleading. It turns out. Um, it's like that's when you first created it, not when you last worked on it. So I often found myself befuddled by the dates. I'm expecting to, say, well, I know I worked on that program, yesterday, and where's the one with yesterday's date? Yeah. Oh, you can't see what I'm looking at anyway. I'm looking at the dialog window for opening a buggy program. Well, it's actually it should be PPP, right? I think I changed the name to 6.3 exercise 3, right? Okay. So this file was known, I should say, as that. Um, and I think, did we get all the errors in there? I hope so. Um, but yeah, so here's the factorial function. It's a recursive function, right? And recursion is one of the features, a salient feature of our calculator program, right? Why? Well, because expression calls term, term calls primary, and a primary could be an expression in parentheses. So um, expression ends up calling itself through the call to term, which calls primary, which can call back expression. Okay, so here we've got the base case. So anytime you've got a recursive function, you almost certainly want some sort of base case, right? And in this case, that's if the input is a 1 or a 0. Then I'm going to return 1. So factorial of 1 is 1. 1 times itself, I guess, or just 1. 0 factorial is also 1. And why? Well, it's the number of ways of putting 0 things in order. Yeah, I know. I suppose just accept that it's the value of 0 factorial is 1 because that's the value that works. Okay. Otherwise, if it's not one of these base cases, then I'm going to return, and I'm going to cheat here. Is this cheating? What if D is not an integer value, right? It could be a double with an integer value or not, right? Does it have digits after the decimal point? Non-zero digits. And if so, we're just going to trim them off and forget about them. What else could we do? Well, there are more complicated answers to what do you do about the factorial of a number that's not an integer, right? Because, n times n minus 1 times n minus 2, if it's not an integer, you're not going to end up with times 2 times 1 at the end, right? So there's actually something called the gamma function, which you will encounter in second semester calculus, which will handle those sort of things. But we're just going to take the simplified approach. And so if you get, say, factorial of 3.1, that's going to return 3 times factorial of 2.1, which is factorial of 2.1 is going to return 2 times factorial of 1.1. Oh, does that not work? Oh, yeah, and the integer part of 1.1 is 1, right? So that will be the base case, right? So I have these integer casts here that will get rid of the decimal part, right? So, yeah. And so what do we do if we encounter a factorial? Well, we need to have our let's see. Can I look at what do I got here? I guess primary. Let's look at the get function, right? And right. So here's token streams get function. We now have a factorial on line 104 here as one of the operators. Okay, so we can create a factorial operator token. And how do we handle that? Well, so primary is the one that's going to handle it, right? So we're going to think of a factorial as a primary. Ultimately, a factorial will resolve to a single number, which is a floating point literal, right? So when we come down here to primary, here's how we're going to handle it. And notice we also now have the opening and closing curly brace, right? Which behaves, they just got to pair up, right? So if you have an opening curly brace, that should be paired with a closing, with a closing curly brace, right? If we get a number token, I think before we would just return here, right? Return the numbers. Oh, in fact, that's my comment. We're not going to return, we're going to get the numbers value, right? We're not ready to return it yet, right? Why? Well, because we want to look ahead one character. Is that primary number token, I should say, is that number token followed by, so we get the next token after the number token. If that's an exclamation point, well, first, if it's not an exclamation point, then just put it back, right? It's going to be the next token you're going to want to get, and it'll now be in the buffer. If it is an exclamation point, then we will get past this if statement, right? So this will be false here. If this is false, then you're going to execute this statement. So, I mean, I suppose we could put an else here, but no need really, right? Because if this is true, then we're going to return D. If it's true that we don't get a factorial, then we're just going to return that number value. Otherwise, we're going to return the factorial of that number value, and that's the way we process the factorial. Yeah? So that's going to work fine. Shall we run this and see that it does? And then it'll be time for a break, huh? So here's my output window. I'm going to enter in, well, I don't know, how about curly brace 1 plus 2 times parenthesis 3 plus 4 times 5 close parenthesis minus, so now we're going to have, should we do a factorial on that? So what's the factorial going to act on here? It's going to act on the result of what's in parentheses, which is 23. 23 factorial, that's going to be fairly large, but I think it's right at the edge of what's manageable maybe, right? And then I'm going to subtract 100 for good measure. Have another curly brace to match the opening one. And should we do divided by 2? And we get a number. Okay, and it is a fairly large number, right? Shall we check that with the calculator? I'm sorry, the calculator window is not showing. Do I have a way of entering this into my calculator to check it? I think in the calculator, do I have to say clear? I have to put a parenthesis. Oh, I got now two parentheses. Okay, so whoop, I'm going to say clear again. Okay, so now open parenthesis, 1 plus 2 times, open parenthesis, 3 plus 4 times 5. I'm just checking to see if this is in the ballpark. Factorial? Oh. Overflow. I think, yeah, I didn't, okay. Let me try that one more time. Sorry. 1 plus 2 times parenthesis 3 plus 4 times 5 close parenthesis. Now I'm going to hit the factorial button. Okay. Minus 100 divided by 2. And I'm getting 25852 as the first digits, and it's can I go to exponential mode? Yeah, times 10 to this exactly. Well, I mean, I get more digits with the Microsoft calculator, but yeah, so that's looking correct, right? And it's waiting for another expression, right? So how about 0.1 factorial semicolon? That's 1. That's good. How about negative 1 factorial? Primary expected. Okay, so what's going on with that negative? Well, it doesn't expect to find a negative at the beginning, right? So let's handle that, because that turns out to be something primary is going to do, right? So if we go to our code, if primary, where is primary? Here. If primary gets a negative token, what are we going to do? And shall we just do that early on here? So yeah, so primary is going to get the negative token. And we're switching on the kind, right? So I'm just going to handle that first, right? So I'm going to say case, and this is, there is a negative token, right? So in that case, what are we going to do? We're going to return the negation of primary. That should work, right? In fact, we could stack up a bunch of negatives there. Let's see if it compiles. Okay. So now, oh, output here. And I'm going to say negative 1 minus 1. That's negative 2, right? Which we couldn't do before. What if I say positive 1 minus 1? Primary expected. Okay. So we can handle that case too, right? So I'm going to say case positive sign. In that case, I just want to return primary. Yeah. So here's the output window again, and I'm going to say minus, plus, minus 1 or 2, whatever. So that's 2, right? 2 negatives make a positive. Yeah, yeah. Okay, on that note, that was an example of 2 positives making a negative, because the connotation is dismissive. Any questions about anything before we take 10 for lunch, or whatever you're doing? It's not enough time for lunch to clear one's mind. I have a cue for quit, huh? Okay. Oh no, primary expected. Huh. That doesn't seem like the right behavior, does it? Wasn't Q the quit token? Have to see about that. Okay. All right. So if we go back to our browser window, we can see, yeah, so you can go ahead and watch that, but I guess the next thing would be to see what's on the docket for oh, so this name value pair thing, this is in anticipation of variables. We're going to want to create a list of variables that we can assign values to and that sort of thing. So, seeing no questions, we'll take 10. So back in a bit. OBS, but not on the other one, huh? Okay, in any case, yeah, so you would just add to the grammar a definite article, so you can always precede a noun by a definite. So a noun could be defined as either a noun or a definite article plus a noun, right? So let's skip over the English. English is too complicated. Write a grammar for the bitwise logical expressions. Oh yeah, this is a good exercise, and I keep forgetting how to do this. So let's investigate that so we can all have it for future reference. So this is exercise 7. Okay, I'm going to go over to the code window and exclude this. We're done with that, right? And then bring in a new item, which is going to be PPP 6 exercise exercise 7, and statement of the problem. Right, so the operators are the negation operator, the complement. So what's the complement of a bitwise expression? Well, what's a bitwise expression? It's an expression with zeros and ones in it. So the complement, you take all the zeros and make them ones, and take all the ones and make them zeros. And is the the usual logical and. 1 and 1 is 1, but 1 and 0 is 0, and 0 and 0 is 0. The exclusive OR, okay. So there's operator precedence, right? So the exclusive OR binds tighter than a regular OR, and the parentheses override that, and the ampersand operator, that's the logical and, binds tighter than the exclusive OR. So yeah, you can see that this expression, then the y and z operates first, and you can sort of make that more explicit by putting in the not sure why the okay putting in the parentheses explicitly to emphasize the ampersand logical and binds tighter than the exclusive or, which binds tighter than. So we have three levels of operation, which is a little bit different, right, than arithmetic expressions. In that we have only two levels really, aside from the parentheses. You have multiplication and division left to right, that binds tighter than addition and subtraction left to right. So can we take existing code and modify it? Can we take our existing program and modify it to have these operations? Sure. Let's see how we would do that. I guess I'm going to go looking for that, huh? So I'm going to, what happened there? I guess I want to file, open, file, and this is PPP 6.3. Okay. This is not part of our project, right? But it is here for us to look at and copy from. So we're gonna not, the factorial doesn't make sense, or does it? Maybe it does, huh? Can we take the factorial of a bitwise expression? Sure, it's just another way of representing a number, except, yeah. Well, let's not worry about the factorial at this stage. So we're going to want the token. We're going to want the token stream. We're going to want the get function as part of the token stream. We're going to want all these things, right? Although I don't know if we want to call them terms. That may need some modification. And we have this try and catch thing going on, which don't really need that either. Oh yeah, actually that's nice, so that we can recover from our errors, right? So I'm going to copy this and paste it in here, and then see about modifying it. How are we doing? We've got comment from Jonathan. In Unix world, 8 spaces for a tab is normal. Okay, that's interesting. I was complaining about the 8 spaces, right? And Jonathan also says, for the SIR project, is that due today, and what do you want turned in? Yeah, I did want to talk about that, so let me add that to our list of things to talk about. We are almost out of time. It's 12:03, yeah, and we're sort of embarking on a large project here. So let's see. Do we have? Oh. This is, what happened to my agenda? Maybe I didn't post it. Or is it down here? Oh no, it didn't. Huh. Oh, I guess I didn't save the agenda? Yeah, that's what happens. Okay, so let's put in a little agenda here again. And some of these, the Kattis warm-up, how did that go? Oh, we're still working on that. Kattis warm-up, and this is descending permutations, I think. And then the book learning, chapter 6 exercises. Looks like we're not going to get much past that, right? But let's also talk about the SIR project objectives. So yeah, I will make time for that. That shouldn't take long. And we do have a little discussion on that. So yeah, I'm going to post this so that I don't lose it. All right. I guess it then appears at the end. Is there a way of like changing the order of these things? Move up? No? Okay. I guess they're in sort of 12:04. There's time stamped, right? This was 11:54. All right. So back to the code. And so yeah, so now we're gonna have we kind of want to talk about the grammar, right? That's the sort of the big picture here, right? So Um, um, so what is a primary? Well, so expression could be either a primary or a primary or an expression. And sometimes I forget which. Or should we say a expression or a primary? Um, yeah, so that we have terms and will allow me to do a little research here. The thing is, I've solved this thing before, right? And where would I find where I've solved it before? Only I know for sure, and I don't know. So, okay. I guess I want to go here and okay. So I want to go here and yeah. I wonder if I can get it. Okay, so yeah. Hang on a second here. I'm going to my directory where this should be, and it is COD site 7A fall 19 code. Is the bitwise thing in here? Maybe I can just search for bitwise. Yeah. Okay, so that's from 2016. Okay. I'm going to open file location. Okay. And I'm going to open this with Notepad. Okay, well, this is just a this is not the calculator. It's just a little sandbox. But I think this will be good for us to get started on this. Okay, so yeah. Oh. Um, so I guess I'm just going to comment out all this stuff here. Can I do that just with one fell swoop here? That's a lot of commenting out, isn't it? Probably it'll interfere with some other things. Oh yeah, there it all goes. Just one big long comment. Great. So then I'm going to paste in this code. And this should give you some idea of the kind of things that are involved with a bitwise calculator. And we're going to include the library bitset. And that will allow us to create bitset objects. It's a template library. Um, I guess it's a template class. So when you say bit set of 4, um, that's saying I've got a 4-bit number. And in base 2, 9 is 8 plus 1, right? Which is 2 cubed plus 2 to the 0. So you see there's its base 2 expression for 9. And so foo is a variable of type bit set with 4 bits, and it's initialized to the decimal value 9, which means that it's going to look like this in base 2, right? But then if we have bar here, which is going to take the string, so interestingly, this bit type can take a string as the constructor. I guess it better be a string which looks like a binary string. I had forgotten about that. Okay, so what we're going to do is, so here's foo, here's bar. Bar is the number 3, right? 2 plus 1. So if you do an exclusive OR with 9 and 3, you can see what that looks like over here. So 1, where can I make this more clear? I guess I'll try to do it. Well, let's do it up here. So this is the exclusive OR, which means 1 or 1 is 0. So one or the other, but not both. That's the exclusive OR. So if you have 1, 0, 0, 1 exclusive ORed with 0, 0, 1, 1, then you're going to get, well, 1 exclusive OR with 1 in the 1's place is 0, right? Whereas 0 exclusive OR with 1 is 1. 0 exclusive OR with 0 is 0, and 1 exclusive OR with 0 is 1, right? So you're going to get, is that the number 10? I guess so, right? 8 plus 2. So what is it going to, we're going to then actually insert the result of the exclusive OR operation into the output stream and see what we get. Should we do that now just to make sure that that first one is coming out right? Wait, does it even compile? Yes, it does. Okay. And here's the output. So you see, yeah. Right, so there's the exclusive OR operation. Then we're also going to get the AND operation. So 0 and 0. So it just goes bitwise, right? Each bit has its own bitwise operation. So I mean, I suppose you could think of this as 9 exclusive OR with 3 is 10, but it doesn't make sense arithmetically, right? It only makes sense bitwise. And the regular OR is okay with them both being 1, right? And then, oh, this is interesting, shift 2. So that looks like the insertion operator, but in bitwise world, that's the shift operator. So that this is saying shift 2 to the right. Yeah, so if you take 1, 1, 0, 0 and shift it 2 to the right, I'm sorry. What does that 2 mean there? Let's go back to the code, huh? So, yeah. Oh, okay, so we're taking foo, which is 0, 0, sorry, 1, 0, 0, 1, and bar in here at all, right? Because this, what is this operation here? This is saying take foo, which is 1001, and shift to the left twice. And so things that, like, so the 1 in the most significant digit, oh, you see. See, bar is not involved in this operation, right? So I don't know why I have bar on the left side here, right? So I'm seeing out foo, which is going to be 1001, and then I have this string, and then bar, which is going to be 0011, and I'm saying that's what you get when you do this operation, which is, I think, shift. I think that's actually shift to the left 2, right? So if you took this and shifted it to the left 2, you get 0100. And this just doesn't make sense then. What is this comment? Shift left, right? SHL is shift left. And with the assign operation. And so that, why is that 1100? That's more like bar shifted left by 1, right? By 2. And in fact, that's what we're seeing, right? Very confusing, right? Because this is the insertion operator. This is the shift left operator. And we're shifting left by 2? And getting, okay, well, maybe we'll try to make sense. I know we're running out of time, I know. So then this is shifting right by 1. So if we take foo and shift right by 1, well, it's already been shifted off its mortal coil. Sorry. So, okay, well, let's run this again, and it's thinking about it. Okay, I think maybe I didn't stop it before. It was still running or something. Okay, I'm going to run this again. Oh, okay. So well, this kind of makes sense, right? Well, if you were to take this and shift it, well, if you were to, nope, none of this is making sense. Let's skip on to this one. I'm not sure about this shifting. I'll have to review that. This is the complement operator. So the complement of 0011 is 1100. That makes sense. Nice to have something that makes sense. So if we shift right, sorry, that must be shift left 1 of 0011, you get 0110. That kind of makes sense. Shift right 1 of 0011, the 1 in the ones place just disappears, right? It shifts off its mortal coil. And then, so are these two bitwise things equal? No, so that's false. Are they not equal? Yes, that's true. You take the AND of two bitwise things and you get what you expect, right? And the OR and the exclusive OR are all there. Okay, well, so I'll post that up as something for further discussion, and maybe we'll have some analysis of why this shift operator does what it does. Okay. And with that, let's go to the discussion of the SIR model. And what is expected to be turned in today, because it's time for a new project, and I haven't posted what that is yet, but I will. Um, Maybe Bulgarian solitaire? Anyone? Well, we'll think of something. Um, Meantime, oh, where am I? Here. Okay. So if we go back to the discussions page, the graph is optional. Yeah, I did create a graph, but you don't need to, right? You just need to create the, well, shall we have the statement of the problem? Let's see, so if we go to here, you can see that basically you just are responsible for producing these three populations. And if you wanted to go a little bit further, this is not required. But these are what? Each one of these lines is the next day, right? So that's our unit of time increment is a day. And so on the first day, almost everybody is susceptible. Um, there is a tiny fraction of the population that is infected or infectious. And, oh, well, yeah, everybody's susceptible. Well, everybody except one person, which is such a small part of the population that it comes out that it just rounds up to one in that case, right? But then you see the infectious population growing until it stops growing, right? And I think that's what I'm doing here, is I keep looping until I get to a place where instead of, so you see here the infectious have actually grown from 0.0658 to 0.0659, and then it shrinks, right? 0.0653. So that shows you're at the point where the cusp has finished increasing and started decreasing, and should continue decreasing from there on out. So then this graph, no, this was not required. If you wanted to see the graph, you can do that, and you should end up with something that looks like this. Did I open that? Yeah, but you don't see it, right? Is there a way of seeing this picture? Well, if you should be able to open that on your end, and you see the first half. Yeah. So the answer to the question: just submit your code, and don't submit it on Canvas. Just email it to me. I saw Alfredo submitted some Repetend code on Canvas. I didn't expect to see it there. I was surprised. Oh my goodness, there's code. Um, so just email it to me. That's where I expect to find it in the email folder. And that looks like, let's see. Oh, wrong browser. That looks like this, right? And you can see, oh, so a bunch of people have sent me some code. That's good. I'll look for that. And I guess, if you wanted to have some further commentary about, what happens when you change the parameters. You can break this thing. I don't know. um, and obviously, people have much more sophisticated models than this one, right? For how you actually do analysis on this sort of thing. But yeah, that then leads open the question of what's next, and stay tuned. I will have something posted soon. So I guess that we got like 5 minutes still. Any questions about anything at all further on? We have more quizzes available, and I haven't really figured out how to manage this thing. So if I go to assignments, um, the Repetend project is here, but then it doesn't appear in grades, so I'm just going to have to do the grades separately and um, post those separately. So I wouldn't pay much attention to the grades thing here, and I will make that more obvious. Um, the problem with the grades is that, if I post everybody's grades together, then there's a certain lack of privacy. Um, there's so few of us to where I can just sort of, easily give everybody their individual report at this stage, which I don't have a lot of Repetend submissions, so I would appreciate seeing that sooner rather than later, since I'm kind of feeling like I've processed that, and I would rather not have to remember how that goes. Which was essentially the division algorithm, right? So if you remember how to do that from grade school, that's all it is, really. The Cannonball quiz, I think I still have to read that. So let's see, starter code is here. Preview is that, so yeah. There should be some way. Show quiz results. Okay, so I see 1, 2, 3, 4 people have turned this in, and I don't think I've read them yet, have I? Because this one, I think, involved a certain amount of hand review, right? Moderate the speed grader. So yeah, I can go to the speed grader, and this student does not have a submission. That's Guillermo. James. Alfredo has done something here, and so yeah, I haven't read these yet, or I don't think I have. Sorry, but yeah, so graded 311, it says. Yeah, that's not true, right? I think that's an automatic grader. Oh, look, looks like I made a comment here. What is this is for the human cannonball, huh? All right, it's been a while, so I'll have to go back and review how I'm doing with that. But yeah, stay tuned. We'll have more to say about all that on Wednesday. I have office hours, I remind you, tomorrow. Not sure what's happening with the Mesa sessions, but well, maybe I should mention this, which is there is the what is it? It's Discord. Do I have Discord on here somewhere? Here it is. Okay, can I get a Discord window? You might inquire. And let's see, can I add a Discord? What if I go to the calculator, which didn't work, and say, yeah, add a window capture. I'm going to say Discord and see if I can make that happen. Okay, and do I see, oh, there it is, Discord. And if it's like everything else, it doesn't work. Yeah, I'm not sure why some windows just don't communicate with OBS, but that appears to be the case, huh? Yeah. Not sure why that doesn't behave the way you would expect it to. Yeah. Okay, well, I'll investigate that. But let me say this about that, which is that there's a way to invite people to Discord. Let's see. I did this before, and now I've forgotten how to do it. Permanent invite link. Okay. So I'm going to copy. Oh. Permanent invite link. Okay. I'm going to copy that, and So I think, Discord is a nice way of getting, help from your peers online. So let me make this evident in today's discussion, which is up here. Um, okay. Um, I need to get out of here. And here, okay. All right. So there's that. Um, and today's discussion. So let me just say here, here's your Discord invite. See if you can make this work. This is for the COD page. Oh, it's. Oh, okay. What happened here? I guess I have to change the font to make it visible, huh? Text color? Okay, so the text color, no, that doesn't do it. How about the background? Nope. It's very disconcerting when they. Alright, I don't know what happened there. Go back. Somehow I clicked on insert equation. Alrighty, I didn't get to post that after all. We are out of time. So let me just say here, that's weird, huh? Can I go here and say, nope. How about here? Nope. All right. I mean, all you need is the text there, right? See if you can make that work. That's supposed to be an invitation to join that Discord group, which might be a nice venue for chatting. So give it a try. So any other class ends at 12:05? Oh, you're right. Why was I thinking 12:30? That's what Jonathan was on about. Okay, I have overbegged your indulgence, and I will. Yeah, the SIR code is the SIR code is due today, right? Please turn that in. It should be fairly straightforward. All right. Sorry for going over. I got it wrong in my head. It was a long spring break, wasn't it? Okay. Well, have a pleasant afternoon, and I will see you Wednesday, if not sooner.